Hello everyone, my name is Siraj, and today my team, Asma, Huda, Khadija, and I will present our project titled Multi-Floor Autonomous Lab Sample Delivery Robot. Currently, lab transportation in hospitals is still done manually across departments and floor. Transport can account up to 60 to 70% of the total lab turnaround time, making it a major source of delay. This process is ineffective, especially in large multi-floor environments. Existing robotic systems are still limited. They operate on a single floor and cannot use elevators or move between floors. As a result, true end-to-end automation does not exist today. Manual transportation increases workload, delay results, and can affect clinical decision in some time-sensitive cases. It also exposes healthcare workers to potentially infectious material. This aligns with the SDG 3, which focuses on improving healthcare safety and efficiency. Therefore, there is a need for a safer, faster, and fully autonomous solution. To address this, we propose a multi-floor delivery robot that navigates indoors and outdoors, uses elevators, and securely transports lab samples without human assistance. Recent research shows the progress in hospital delivery robots. Some systems are deployed in real environments while others focus on safe navigations with minimal human interaction. However, most solutions still lack vertical navigation, operate only indoors, and depend on building infrastructures. To overcome these limitations, our work introduces indoor and outdoor navigation, using LiDAR and RTK vision-based elevator interaction, using a custom UAE dataset, safety verification, and end-to-end delivery workflow from pickup to secure delivery.
This is a system overview of our multi-floor lab delivery robot. Before the robot can autonomously navigate in a building, it needs to know its environment. To do this, it uses LiDAR SLAM mapping to scan each floor of the building and generate maps that are stored inside the robot with the corresponding floor number. Using these maps, the robot begins its mission from home station, which is used for charging between deliveries. Once it receives a task, it uses its planning algorithm to navigate to the pickup location. Now, at the pickup loop point, the authorized staff unlocks the delivery compartment by scanning the QR code or using an access card and place the items inside the compartment. The delivery compartment itself is designed to securely store and protect lab samples during the transport and delivery, including maintaining appropriate conditions and preventing unauthorized access. The robot then navigates to the elevator and positions itself in front of the elevator control panel. It captures an image, processes it using an object detection model, and outputs the prediction for the up and down buttons. Then, using simple decision making and kinematics control, we can get the arm to press the button. The robot then continuously monitors the elevator doors, for them to open. When the doors open, the robot checks for available space before entering. Now, inside the elevator, it repeats the same process using object detection and OCR to identify and press the correct floor button. It also performs a verification step to ensure that the button press was successful. During the elevator ride, the robot switches between the current floor to the destination floor using a ROS multiplexer and initializes its position relative to that elevator. Before exiting, the robot verifies that it has reached the correct floor using multimodal verification, combining between sound cues and visual cues. It then exits the elevator and navigates to the delivery location and prompts the staff to collect the delivery using a mobile phone. Throughout the process, a mobile application allows staff to monitor the robot's location, track progress, and receive updates in real time. Additionally, for outdoor deliveries such as transferring samples to or from ambulances, the robot fuses between LiDAR odometry, wheel odometry, and IMU to navigate accurately in outdoor environments. We face several challenges with existing datasets online. These challenges include that most datasets do not capture the variability in the elevator button designs and indicators. They are also not collected from the robot's camera perspective, and they do not account for regional differences between countries. To address this, we collected our own dataset consisting of 90 UAE elevator panels captured directly from the robot's point of view, totaling around 3,300 images split into training, testing, and validation. We trained a UNO V5 detection model on this dataset to detect elevator buttons from the robot camera view and generate bounding boxes for each button. However, detection alone is not enough, since we also need to know which button corresponds to which floor. For that, we use an OCR algorithm to recognize the numbers on each button. To improve robustness, we apply multiple processing techniques and select the highest confidence OCR result among them. We then match OCR outputs with the target floor and select the correct button to press. After selecting the target button, we use a button localization script to actually know the correct center of the pressable button in that image and obtain its image coordinates in terms of U and V. The image coordinates are then projected into 3D camera coordinates using the camera parameters. After that, we apply coordinates transformation using matrix multiplication to convert these points into the robot space frame. Using this position, we apply an inverse kinematic solver to compute the required joint angles Q1, Q2, Q3, and Q4 of the robotic arm. The solver uses a Jacobian-based iterative method to minimize the positional error between the end effector and the target button in the robot's base frame. Once the joint configuration converges, the arm is actuated to reach the target position, and the end effector performs the button press. After execution, we perform an illumination-based feedback check to verify that the button has been successfully activated, enabling reliable closed-loop interaction.
For outdoor navigation, the robot uses a multi-sensor localization framework integrating LiDAR, wheel odometry, and an IMU. LiDAR performs scan matching between consecutive scans to estimate motion by aligning point clouds and capturing environmental changes, while odometry provides relative displacement and the IMU supplies orientation data. These measurements are fused using an extended Kalman filter, which applies prediction and update steps to estimate the robot's position and heading. The prediction uses the motion model, while the update corrects the estimate using sensor data and the Kalman gain. This approach improves robustness by handling noise, drift, and temporary sensor degradation through uncertainty-based weighting. To support real-time operation, we developed a mobile application that allows staff to monitor and interact with the robot. The app provides real-time tracking of the robot's location, along with the status updates throughout the delivery process, including pickup, elevator interaction, and final delivery. It also displays the robot's route and estimated time of arrival, allowing staff to follow the delivery progress easily. This ensures better coordination, transparency, and efficient management of delivery tasks within the hospital environment. Moving on to the results.
This work is evaluated across three main aspects: end-to-end task execution, including navigation, elevator interaction, and successful delivery completion, detection and recognition performance, assessing YOLO V5 and OCR accuracy in identifying the correct elevator button, and localization stability, measuring the consistency of EKF-based position estimation in real-world dynamic environments. The AI model achieves 94.5% precision, 95.8 recall, and an MAP of 96.74% with an F1 score of 95.17%. The precision recall curve remained consistently high across thresholds, showing stable performance and good generalization. The confusion matrix shows 1,559 correct detections with 41 false positives and 383 misdetections, indicating strong overall reliability. These detection samples shows accurate performance under different lighting conditions, angles, and partial occlusions. Next, we evaluate the full autonomous system in a real-world scenario. This demo represents a real-world hospital logistics workflow, where an autonomous robot transports medical samples between an ambulance intake area and a laboratory. The system is tested in a standard indoor-outdoor building environment, simulating real hospital conditions. The robot begins at the pickup point and navigates using LiDAR, IMU, and wheel odometry, ensuring stable localization. It transitions from outdoor to indoor navigation, maintaining continuous pose estimation. It then works through the corridor, approaches the elevator, and enters the elevator. Once it positions itself inside the elevator, the robot starts using OCR-based perception to detect the correct target floor button, and the robotic arm autonomously presses it. After reaching the destination floor, it exits the elevator and continues navigation towards the final goal. This demonstrates a complete autonomous pipeline combining navigation, perception, and physical interaction. The OCR system successfully detects all button regions and correctly recognizes button 13 with a confidence of 1, consistent across pre-processing methods. Now, moving on to the conclusion and future work.
In conclusion, our system demonstrates a practical solution for autonomous lab sample delivery in multi-floor environments. It integrates navigation, perception, and actuation to enable reliable real-world operation. Overall, the results show strong potential for reducing manual workload and improving efficiency in hospital workflows. For future work, we plan to extend the systems to support multi-robot coordination for scalable delivery operations. Thank you for listening.